In this research spotlight from all the bachelors, we look at a recent paper on 4D printing, posted in March 2026 by Iqbal and colleagues. Its headline idea is simple but clever. Get a printed object to program its own shape-changing behavior while it is being printed, using just one material, in a single step, on an ordinary desktop 3D printer. First, a quick reminder of what 4D printing means. You take a normal 3D print, but you design it so that later, when a stimulus such as heat is applied, the object changes its shape on its own. The so-called fourth dimension is time. The transformation is built into the object from the start. This lets a flat, easy-to-print part fold or curl into a more complex final form. Here is the usual catch. Most shape memory 4D printing needs a separate programming step after printing. You print the part, then you physically stretch, heat, or deform it and fix it into a temporary shape. Only later, when you trigger it with heat, does it recover. Those middle steps are manual and fiddly, and they become very hard to do for complex or delicate structures. The paper's central idea removes that hassle. The authors use a method they call programming via printing, or PVP. Instead of programming the shape memory afterwards, the strain that drives the shape change is trapped directly during printing. In other words, the programming happens as the object is printed. There is no separate shape-setting step, a single material, on a standard desktop fused filament printer. How much movement can this produce, and in which directions? The trap strain naturally makes the material contract when it is heated, and the authors report programming large, spatially controlled strains up to about 50%. Contraction alone would be limiting, so they also engineer expansion by designing architected lattice structures with patterned strain. Combining the two gives a full range of deformation modes, not just shrinking. Why does this matter? 3 things stand out. It is accessible because it runs on ordinary desktop printers rather than specialized equipment. It is low cost and simple, using one common material with no special post-processing and no error-prone programming step. And it is scalable. The authors validate the behavior at the level of single-unit cells and then combine those cells into larger proof-of-concept structures. As always, a few honest caveats. The actuation here is one way. The structure transforms once, rather than cycling back and forth. The results are proof-of-concept demonstrations, unit cells and example structures, not yet a finished product. And this is a preprint on arXiv, so it has not yet been through full peer review, which may still refine the details. That said, moving the programming into the printing step is a genuinely neat idea. So here is the takeaway. By trapping shape memory strain while the object is printed, a single material on a cheap desktop printer can be made to morph on command, with no separate programming stage. It is a small but clever step toward making 4D printing something you could do on an everyday machine. If you want to see the original figures and data, follow the link to the paper. Thanks for watching this research spotlight from all the bachelors.